Oh, did I write the due date correctly? I'm not sure. Might have messed up on the due date. I posted a new homework, but I have no memory of when it is due. So there is a good chance that I did not change it from last. So I cut and pasted from last year and put it here. So I think I might have not changed the due date because at least I don't have a memory of either I forgot or I'm getting old. So there's a homework 9, which I posted. So at this point, everything that is before homework 9, the due date is crossed. So now it's everything is what you call bonus. In a sense, it's all your responsibility. Don't delay it too much. April 30th is too late. Okay. April 15th is late. April 15th is late. So have April 10th or something like that as a deadline for yourself. But if necessary, don't get sick. Instead, take the extra days. Like, don't get stressed. If you don't mind me telling that too. But you're taking it in the right spirit, right? As of now, Rob.
Oh,
Like,
believe me, we had a meeting last night, a dinner meeting with some faculty and our chancellor and the human resources director, and I was the center of early comments. And during the dinner, I thought about something and I grabbed for my phone because it was in my pocket of my shirt, and the HR director was like, "Don't do that." Like, just grabbed my phone to check a date.
So this is due on Tuesday. So 2 lectures, and so that's 5th, so April 12th.
What is the topic of this homework? Kepler?
Kepler, yeah. So we have 4 weeks remaining at this point. 2 weeks Kepler and 2 weeks special relativity. And I have to be a little, I have to try to keep the deadline, otherwise to miss something. I always have this option that I can go fast and make you guys go and look at the videos from last semester, but it's not effective. Like, I noticed that that's something that I have to seriously consider. From my perspective, during spring break, I am saving time by asking you guys to go and look at 1 hour of video and give a homework based on that. But I think from students' perspective, it really throws you off because it's a one week, one extra homework you got, which probably you won't do it during spring break because you probably have a family or just relaxing. So I think maybe that's not a good methodology. I'm not sure. So that's something I'm reconsidering. And same thing here. If I miss it, I can use that option always, but I'll try not to. It's probably better to have extra class. We'll see. I'll try to finish it. It's always a question of jumping steps, right? You just have to jump a lot of steps. Okay.
So we have class in May.
No. I think April 29th. Okay, today is what? 5th, right? So 7th, 8th is a Friday. So add 21 days. 29th is the last day of classes. So 29th is last day. So 30th is a Saturday. May 1st is a Sunday. And then you have the exam. Does that help?
Yes.
So the last week of the semester usually is, we call it exam week. So you have 5 days of exam week. So whichever day your exam is, that's when you take it.
Is it Friday, the exam?
I think so.
It's there on the website. I don't have it here.
May 3rd and May 5th are Tuesday and Thursday. That's nice.
No. April 29th is the last day of classes in the whole university. After that, I cannot have classes, even if I want to, fill the curriculum or anything, I cannot have classes. It's a university rule because students might have exams on another day. So the day I have my classes might affect some students in the class. So I cannot legally have class in with a strong advice. And I cannot have anything due either after 29th. So that's the procedure. So you have an exam week, which we argued that it is on May 2nd is a Monday, right? So calculate, so I think it is 6th is a Friday, I guess, right? So 6th is a Friday, 7th is a commencement, and the semester is over. You can go home. And it's
Our
about
exam is 6.
6, yeah, okay, so it's a exam is on Friday, and it will be that particular time. It cannot be changed because it's a like different students might. Here it is easier because it's 5 students. At least once I have had a case where everyone gave it in writing and I moved the exam. And if you give it in writing, then even that is discouraged by the university. But in a graduate level class, at least once I have done this, but I will really discourage it, and it can lead to trouble for everyone in principle. But again, 5 people, the chances are low. But if you have a class of more than, or what I go by is that if it's an undergraduate class, I don't even entertain. There's no question. Because they have too many things going on. They take 6 courses and some of them are working. So there's a lot of things that affects their schedule. Then graduate level is slightly more, at least schedule wise, it's more relaxed. Concepts wise, probably you're more stressed. Does that help? Philip?
Yes. We have the quantum exam, I guess, on Thursday evening, and then in the morning we have class.
Yeah, I think good point. So that's the challenges. I would say at this point, I think we are responsible enough that like before that, you don't have any exam. Right? That's also true. Like from Friday to Thursday, you have nothing, correct?
Yeah.
So you just have to get responsible and divide your time properly. I think that's better than me trying to change or Dr. Bird trying to change. It's a lot much better. And by this time, we should be responsible enough to schedule our time properly. That's what I would recommend. If it was one back to back, then probably I would have given it a thought, but still I would says, okay, be responsible. Like there are sometimes undergraduate students who have 3 exams in a day. It's just based on their timing and what courses they take. So they have brought in a new exam scheduler. So earlier the exam schedule used to be announced in the first week of classes. These days it is announced in the 5th or 6th week in the classes. So this is a program apparently, which based on the enrollment of all the students in the courses, they find the minimal number of students having 3 exams instead. So that's the only purpose of the program, that they will schedule the exam in such a way that the number of students who have 3 exams in it, or 3 or even 2, they will minimize it. I don't know how effective it is, but it must be. I mean, one can imagine such a program very easily, an algorithm to do that, and they move around that. Does that help? And then the next semester begins in August, somewhere, I think in August 20th, if I'm not wrong. After August 15th. So that's the summer period for since this is your first summer, and plan accordingly. That's a good time to do research. That's when you should begin your research. See a serious. You can make significant progress during the summer. It's pretty much 3 months. It's more than 3 months. Actually. You count that number. It's more than 3 months. But surely you will have vacations. You should go. You should relax. But still, there is sufficient room to get some serious work started at least. So that's my recommendation. Okay. So this is Tuesday. And midterm exam done. I don't remember the final exam. There is a final exam. If I don't remember the date. So final. Rob tells me it's on Friday. And there is an exam calendar also. If you go to Google and search for academic calendar or actually exam calendar, SIUC, within the first 2 links, you should see it. So there is usually an academic calendar which tells you what are the holidays. There is an exam calendar which tells you the exam dates and those kind of stuff. You should be able to search it. Yeah, that's it. Okay. So, so now that we spent a lot of time on Newton's laws, basically trying to gain more insight on Newton's laws. That's what we did for the whole of about 12 weeks. Again, we are in the same place, that F is equal to ma. We haven't made much progress, but we have a lot of insight as to, yeah, that is a Hamiltonian, there are conserved quantities, and how we can check that something is conserved or not relative to something else. That's a Poisson bracket. But let's go back to our old Newton's law, and our idea is to understand how a planet goes around the sun, or a moon goes around the planet. Any 2-body problem. That's our. So this is popularly called the Kepler problem. Why is it called Kepler problem? Why not the Newton's problem? Kepler solved it first. Yes. In what sense? Solved it. Means?
Based on the laws of planetary motion.
Yeah, he saw the pattern. I think that's, I mean, he didn't have Newton's law, so he couldn't solve it in that sense. So I was just questioning that. Yes, so I think the story is that, what is it, Tycho Brahe? I think Kepler was, you can say Kepler's advisor or boss at that time, however you have that. He did a lot of observations. During those times, kings used to spend money into this. They gave a lot of funding for this research. and he built a nice telescope, and he had lots and lots of data. He got very good quality data, and Kepler was a student. He saw the pattern in this data. So for the different planets, there was no equations, but he got pretty much the solutions as Newton's equation would have given, except that he said these are elliptic orbits. And like he put it in words, that's a pattern. And what are the three laws of Kepler, by the way? The three laws of Kepler, right?
The area surface constant.
Correct. So that's the second law. So what Abdullah is saying, so this is the second law. Very good. So if you so in equal times, the area that it will sweep, so this is T1, let's say T2, and this is time period, let's say T, some division of time. So that's your 2T. The area that it will sweep in equal amount of time will be exactly the same. Completely based on data, remember. You should appreciate in those times when you didn't have equations to see that it's pretty impressive. That's the second law. What's the first law?
The orbit is an ellipse with the
Yeah.
sun at the focus.
Perfect. So when I said this was shifted, right, it's not really circle, it's down. Here, the first law is that it's an ellipse. If the orbit is an ellipse, even that is that should be appreciated significantly. When we say it is an ellipse, so for example, let's say, yeah, so this is a circle, and an ellipse would be you decrease this a little bit and increase this a little bit, right? So that's your, let's say, let me keep B fixed and I increase my A. That's fine. A, that's an ellipse, right? That's a definition of an ellipse. So x squared over a squared plus y squared over b squared is equal to 1. That's an ellipse. So how off are you, like how much would you increase this A, let's say by percentage, if you want to talk about, let's say, Earth's orbit is it circular? Is it elliptic? We say that it is elliptic. But then how much by percentage is A off by B? Is that clear what I'm asking? Right. There is a measure for this. It's called eccentricity. So eccentricity for a circle is 0. Right. And I should say this is 1 minus, either it is b square minus a square or a square over b square. I usually don't remember. Let's keep this b square minus a square. So this is equal to 0 clearly when a is equal to b, right? So this is for a circle. And the question is, how much is it for Earth? Any guesses? 1 is the extreme you can have. It can be only between 0 and 1. Okay. So is it 0.5, 0.6, 0.3?
I think it's more like 0.0 something.
Yes, very good. So it is very small. I mean, it's less than 1%, or I think it's less than 2%. Like if you go by this to be a percentage, between 0 is circle, 1 is an ellipse, so it's only 0.02. So far, it's very good that, or there's a good chance that you will miss that it is a circle. If you were to draw it, it's only slightly. I mean, it's only a very slightly elliptic. Like Earth is not. I mean, usually we draw this significantly for illustration purposes, zoomed out in a sense, or more in the extreme sense. So in that sense, it should be appreciated that the data Kepler could read this in his data that actually is elliptic. So that's the second law. What's the third law?
Was the time that the rotates the square is proportional to the focal radius.
Exactly. So the time period, not this time period, the full time period, it doesn't matter actually. It's all related, right? So time period, time cube is proportional to radius now, I pretend that is A over B over 2. So the average of the two radius, that's R squared. No, this T squared is R cubed. Right? So T squared is R cubed. So again, it was possible only because there was very good quality data. So in principle, all the results were available before Newton and Galileo came over, and it's just that Newton could see the generality in the whole thing. He could give an equation which gives this as a solution, and a ball being dropped in uniform gravity as the same solution. So that the universality of that equation is what makes Newton's equation very important.
Isn't that the third law? Don't they often present that as the semi-major axis cubed?
Semi-major, this one,
For the
A cube?
yeah, for
Maybe, I don't remember. I don't remember. So you're saying this will be, this should be, so if this is B, or this is B and this is A, this should be A cube.
that's how I've
It
seen
might
it.
be, okay.
But I've seen that, you know, there could be the constant proportionality could take care of that.
Could it?
But, well, I mean, if because
Because the way I said it, R is A plus B over 2, correct? So if I want to put an R, I will have to put an A plus B in the denominator, and it may not be that clean. So it's either R or A cube probably, one of them. And what is that correct one?
I've seen it as a cube.
Yeah, it must be right. So Chris, right, that's reasonable to find out.
I think that's a small radius thing.
Yeah, what you're saying is that B minus A is small. A is probably large, B is large. I mean, A and B are relatively pretty much the same in what we are doing, but the difference might be small. And it might be an approximation, but we will see. How about this? As we go down, we should get this as an equation. We will get the equation of the ellipse clearly if everything goes well today, but I doubt that. There will be a lot of discussions that will come up. But next class, we will surely have the equation of an ellipse in our hand, and yeah, we'll see. Yeah, I don't know how this. I think I never derived that. Yeah, good point. Yeah, I think when you do that, always you do that circular orbit, but starting from the elliptic equation, I think I've never done that. Yeah, I did give a homework as to what time of the year do you reach here, right, about that. So in principle, it's possible, yeah, you have a lot of flexibility with that equation, but I personally have never done it, so I don't know. But good question, yeah, is it R or A or is it B, and is it an approximation of how? Okay, so how would you go about doing this? We say we can start with Newton's law, for example. That's one way, but we'll start with the Lagrangian. Right? So Newton's law would say that mass times acceleration will be equal to, and immediately you will say that, oh, that's the mass of what, correct? So you should have a challenge there. So what's the problem we are describing? We have a mass, let's say M2, and there is a mass M1. This could be the Earth, that could be the Sun, and we don't know the orbit. We're pretending that we really don't know the orbit at all. We see that it is elliptic, but we want to say that there are two masses and the only force acting between them. So that's force F12, like on 1/2, and the same thing, that is a force F21. So what we do have is M1, like M1, system M1 experiences an acceleration A1, and the force is described by F12. That's the only force. There's nothing else acting on that. And similarly, M2 times acceleration A2 is equal to F21. That's the second equation if we start from Newton's law. Newton's third law tells that F12 and F21 are equal and opposite. That's Newton's third law. That means this is equal to 0. And of course, Newton's law of gravitation tells us that F12 is equal to G M1 M2 over R squared, where this R is center to center. Both these are huge objects. This is like a center to center. It's not from the surface to surface. It is a center of mass to center of mass. What is the value of G out of your head?
6.67 times 10 to the negative 11.
Okay, yeah, 6.7, right? Or 6.6?
67.
6.7, yeah, 6. Let's say 2 6 digits. Because 9.8 is 2 6 digits, right? So let's work with 2 6 digits. And 10 raised to minus 11. And units would be, I think, Newton meter square, right? Newton meter square over kg square. Seems to be small, but small is always relative to something else, right? Unless you have some other scale, you cannot say something is small at all here. This is the only force. And in fact, masses are significant. So if we compare it with the forces that we experience, that's the only comparison we have. We experience a force of 1 Newton when you're falling, if you have a 1 kg being, or 0.1 kg into 10, right? Acceleration is 1 Newton. So that's the only comparison we have, but this is a different scale altogether in the sense the distances are really huge. We're talking about solar sizes of the solar system, and M1 and M2 is a good thing to have in mind. Mass of Earth, just for reference, is approximately 10 raised to 24, so it's 5.97, I think. So 2 6 digits, it's 6.0 into 10 raised to 24 kg. Doesn't matter the 2 6 digits. What you should remember is in your head, just to have a feel for how things are happening around you, is that this is 10 raised to 24 kg. That's really heavy. But again, that number itself doesn't help you. You always need a comparison, right? So you always compare it with, at least what I keep in mind is that that is Jupiter and that is mass of sun. Like these things are the biggest objects in the solar system, right? If you want to keep the most dominant object, that's of course the sun. And after that, Earth is nothing. Jupiter is the next object. If you want 1% accuracy, right? Even this is just 1% accuracy. If you're not interested, for example, if you're interested in the motion of Mercury, a valid question to ask is, how does Neptune affect it? How does Neptune affect it, or Jupiter affect it, Saturn affect it? Very valid questions, but if you do the calculation, it turns out it's less than 1%. So we don't even care for it in the first level of calculation. But these days, astronomical observations are precise enough that you won't care for all these things. But the important point is that Jupiter doesn't affect. Why doesn't it affect? This is 10 raised to 24. This is 10 raised to 27 kgs. Only order of magnitude, 0 significant digits. And Sun is 10 raised to 30 kgs. Notice 1,000 times bigger, 1,000 times with 3 significant digits, you've gone to the left or to the right. If you have M1 plus M2, only if you have this precise to 3 significant digits or the mass of Jupiter to 3 significant digits, this will contribute to it. Like if you add it, otherwise it will be gone in the error. Same thing with the sun, this is a million times larger. So only if you want 1 in a million accuracy, you want to talk about Earth at all. Like if there is a comet coming towards sun, unless it is really grazing through Earth, if it is just coming, visiting sun and going, Earth is probably just a spectator. It doesn't affect the motion of a comet at all. So that's just, you can argue that based on these numbers. So it's good to always have in mind that 10 raised 24, 27, 30. That's your order of one is 1,000 times bigger than the other. So that's your setup, right? Newton's law would have this equations, and immediately you will put this in, or whatever you do. There are two equations which are vector equations. So broadly, there are 6 differential equations: derivative of x, derivative of y, derivative of z, of one of the objects, second object. But it's not as complicated as that. We will see that it's significantly simpler. And to see that, then we have to, if it is not really 6 coordinates we have to worry about, we have to have the right coordinates, right? That's what we have. That's what the whole build-up of the semester was about. Which are those coordinates? How does that work? So the idea is to find what are the constants of motion and use that constants of motion to get rid of coordinates. Like here, it seems like there are 6 coordinates, right? X, Y, Z of this, X, Y, Z of this. There are 6 of them. That's a lot of equations to work with, even if it is algebraic. Forget about differential equations. It's tedious. But we will use the method of Lagrangian. I will use the method of Lagrangian here in this class. You in your homework will use the Hamiltonian to deal with Hamiltonian equations, and I will use the Euler-Lagrange equation. And we will see that immediately, very quickly, this all boils down to one equation, right? That's only one parameter, which is easy to see, right? It's the angle and the radius r. It keeps going around. In fact, even time is not significant in this. One would think that, of course, everything is happening in time. But a nice point is that anything that is monotonically increasing is a good representation of time. Right? Anything that is monotonically increasing, it doesn't come up and down. Like sine curve is not good. If it's a parabolic curve, that's good enough. And you just need a mapping. Right? Might t equal to 0 is this, t equal to 1 is this. If you have a mapping between a monotonic function, increasing function, bit, and what we usually consider time, that's good enough of a time. And what we will do is that this angle that is going around, that's monotonically increasing. If you allow it to go 0 to 2 pi and allow it to take higher values from 2 pi, it is always going forward, right? Angle always increases, it doesn't decrease. And it turns out that angular momentum is conserved in this problem. So we will use angle as our time, which is what we do pretty much, right? We say, how old are you? We say 42 years. So that is 42 times you've gone around. We do use that pretty much. It's designed in that way because that's the thing we have as a reference. So there are 2 parameters here, radius and the angle, which should be very clear. And angle will be used as a time. We will translate that into time. So radius as a function of angle gives you everything. If you know that equation, and that is the equation of an ellipse. The answer is that Kepler already gave the answer, that radius as a function of angle. So equation of ellipse is a solution to this equation. So problem solved. Kepler actually did it long back. It's just that we want to go through our formalism that we built for 12 weeks. A few more things. If you have angular momentum that is conserved, that's good. So what happens is that if angular momentum is conserved, angular momentum is a vector, correct? And angular momentum is, I'm telling all this as an intuition, like I'm not really using the equations, and I'm trying to give you what Kepler problem involves, like the symmetries in a Kepler problem. So it is possible to show that angular momentum is conserved, which is r cross p. Angular momentum is r cross p, and one should ask here, if you're very careful, what position of which particle and all that. So that details will come to. So there is an angular momentum of the system. Pretend that the sun is really massive, so there is only one particle going around. So that makes it slightly easier to visualize. And what does that mean is that r dotted with L What is that equal to? If angular momentum is R cross P, what is R dotted with L? It's zero, correct? So it is zero. What that means is that if you have an angular momentum, your position of the particle has to be perpendicular. That's your R. So if your angular momentum is fixed, so find a direction, let's say north pole. That's your direction in which your angular momentum is passed. That means your orbit has to be perpendicular to the direction. So that is a plane perpendicular to the L, and the motion is in that plane. So immediately you have brought down one variable. Just because angular momentum is conserved, your motion is fixed on a plane. It cannot go out of the plane if angular momentum is conserved. Okay, that's one thing. If it is a circular orbit, there is nothing else you can do. So it just goes in a circle, there is a symmetry. But Kepler told us that it is not really a circular orbit, it is an ellipse. So ellipse has a direction. Right? Ellipse, if you think of it, so this has a direction. This tip is different from that tip. So there is a special direction that ellipse points at. And one would like to ask, okay, so you're fixed on a plane, does that ellipse move around like that as a whole ellipse? Can it move around? Is that a possibility or not? And it turns out, no, it cannot. It is actually, once the motion begins based on your initial velocity and initial position, this direction of the ellipse is fixed. And that direction we'll call it A. There's a magnitude also associated with it. So the moment I say it's a vector, there is a direction of the vector, that is a magnitude of the vector. So A also is conserved. Okay. And A is called the Runge lens, or let's say Laplace. I think it's Z. That's vector. It's not that they all were in the same period of time. There's a significant difference in the era. So most probably the credit should be to Laplace completely, but Laplace has done so much, so people like to give credit to everyone, even though they independently got it at a later stage. Again, angular momentum means that there is angular symmetry, so that's conserved, but there is one more conserved quantity, and that has to do with the direction of the ellipse. And the magnitude of this vector is nothing but the eccentricity of the ellipse. Okay. So eccentricity of the ellipse is exactly this. In your homework, you will show that this is conserved, right? And you will show that this is conserved. Okay. So I qualitatively gave you all the information. I will not be working on that in the limited time we have. I will not work on it, but we will. I'll directly go to the expansion. Few things, and actually, yeah, it's also good to just as a So this is a quiz. Let us say angular momentum has an algebra, right? So this is quiz. Angular momentum has this algebra, which is Li, Lj, and Poisson bracket, right, is equal to, what is this equal to? Lk, but it's epsilon ijk, right? So give me I and j, and I'll give you the k, which is decided by the antisymmetric these two. If it is 1 and 2, it is 3. If it is 2 and 3, it is 1, and so on. Remarkably, the vector A, the Runge lens vector, also has an algebra. It is not exactly the rotation, that's the quiz part. Right? they want to find that out, what you do is that a linear combination of L and A satisfies, it is like two angular momentum. This is an angular momentum. You can construct two angular momentum out of L and A. And the addition of two angular momentum describes the Kepler problem completely. And you do addition of angular momentum in quantum mechanics. Right? If you've done a reasonable course on quantum mechanics before this, then you would know that two angular momentums can add, and there is a nice algebra associated with that. Given the states, you can do a lot of things with that. Remarkably, the Kepler problem, the whole of Kepler problem is described by L and A. It can be understood as two angular momentum, which is not exactly, this is of course an angular momentum. This is not really an angular momentum, but a linear combination of L and A. So let's say J, right? J L plus, let's say A times A. And so this is J1, and let's say J2 is L minus of A times A. A linear combination of them actually leads to two quantities which behave, each of them behaves exactly like angular momentum. That means to say that they have the algebra of angular momentum. And that means that once you have angular momentum, you know most of the physics of it very nicely. So you know the physics of the hydrogen atom in terms of the angular momentum states. So it's a beautiful concept there. And if you go further a little bit into symmetry, yes. Oh.
What is the last word after that?
Vector. Oh, sorry. Vector, V-E-C. Is that better? Vector. Right. Yeah. Okay, vector. It's just the vector. And the main point is that it is not obvious to see that conserved quantity. It is not even, you don't even expect the symmetry, right? What symmetry leads to this? I mean, once you got that this is conserved, then it was easy to understand that it has to do with the ellipse pointing in that direction. But if you had to reverse the problem, what are the symmetries in a Kepler problem? It's hard to guess that. Angular momentum is more common. It's there everywhere. Every system has angular momentum. This is only in hydrogen atom. You see only in a hydrogen atom. You won't see this probably in. I'm saying hydrogen atom Kepler problem. Yeah, we are doing. I mean, you do so much of quantum mechanics that you keep telling. But classically, it's exactly that. You can say this is a classical hydrogen atom. So, what was I saying? There is angular momentum here. Yeah. Usually, you ask about what is a symmetry, what is a transformation that angular momentum is invariant under, and it is rotations. And as an algebra, you say it is SO3. Okay. Is that a familiar word? It means it is a set of transformations. These are orthogonal matrices in 3 dimensions. Right? Rotation matrices are orthogonal matrices in 3 dimensions, and S has to do with let's say would you say right-handedness? Like you say that I want only the right-handed rotations in picture. So the determinant of all of them is 1. So forget the S, that's detailed. These are all orthogonal rotational matrices in 3 dimensions. That's what angular momentum is. This is also an angular momentum. If I say there are 2 angular momentums, that's 2 SO3 cross SO3, right? So you say this is SO3 cross SO3. And that turns out to be related to SO4. So basically, the 2 angular momentums can be imagined to be a rotation in 4 dimensions. So instead of working in 3 dimensions, you say construct a problem which has rotational symmetry in 4 dimensions, and it gives you the whole of Kepler problem completely. So there's a lot of nice things involved there, but in your homeworks you basically need to just do it, just getting ready for that that, okay, these two are conserved, they exist, so that later on you don't get surprised. When you're doing this, working on hydrogen atom, you put a magnetic field and an electric field in it. And the basic idea is that when you're putting the magnetic field, it primarily interacts with this angular momentum. And when you put the electric field, it interacts with the other one, either the A or it's the linear combination of, I don't know, I think it is the A, because A has to do with the, yeah, so think of electric field interacts with the dipole, right? That's the electric field caps for, or if you have an electric field, it will polarize. An ellipse looks like a polarized atom, right? That's been extended in one side. So this change from circular orbit is what electric field caps for. So electric field will interact with this, E dotted with A, and that's what decides here how an atom will interact with an electric field. Again, it leads to a change in levels and so on. And magnetic field caps for L. Think of spin. Spin, any angle, any angular momentum leads to a magnetic moment, and magnetic moment has interacts with it. So that's a very broad, very hand-waving feel for what a Kepler problem is. It has a one-to-one connection with hydrogen atom, except what? Why couldn't a hydrogen atom be explained as explained using all the ideas of Kepler problem? It also goes around, like if you change G M1 M2 by 1/4πε, right? If you replace G with 1/4πε0 and M1 with Q, that's just letters, right? Variables. What goes wrong? Why was it not sufficient to explain hydrogen atom?
Energy was quantized.
Yeah, exactly. Energy is quantum, or the, I think easiest is that the lowest energy possible, like if you have a field for the number N, L, M, N, right? Those are the energy levels in some quantification and some basis that we use is the N is the orbit, like the lowest orbit, right? S shell. Like that's the lowest thing that comes out. If we do quantum mechanics, the lowest energy possible is for N equal to 1. If you do classical physics, and again do quantization and all that, N equal to 0 turns out to be possible. So that means it can jump in, right, into this. So it will keep going in. It of course happens continuously in classical. So it can go all the way to N equal to 0. There is nothing stopping it at some point. At quantum level, our observation tells us that it cannot go below a certain point. It has a minimum in there. And that's where classical physics fits. And that was big enough that you had changed the whole philosophy of the equation itself. Okay, so that's a good bit of qualitative arguments, but we want to work with these equations, but this is not very obvious because there are 6 variables. Let's go back to the Lagrangian, right? So we'll write the Lagrangian and let's start from the scratch again.
How do you find a equation like that?
Yes, there is an equation in your homework. It is basically the direction, whatever the direction is, that's how you build it. But it's a good question as to, what is, to begin with, how did Laplace discover it, right? That's like, now that we know it, it's in the direction of the ellipse, then it is easy to see that. But he pretty much, so that's why it was Laplace. So I don't know how he came up with that. Yes.
No, we said that once the ellipse is fixed, that the A is a constant. But isn't there at least with Mercury a procession of?
Good, very, very good. Yeah, if it's a 2-body problem, like we are working on a 2-body problem. If Mercury was the only object in the whole solar system, and that is Sun and Mercury will come back exactly to the same point. It will be the same ellipse. It will point in the same direction in space all the time. 2 restrictions to that. One is that it has to be obeying Newton's law. but it turns out it doesn't obey Newton's law. Newton's law is not accurate enough. If you bring in Einstein's correction, you can explain this movement of, so what Rob is saying is that, so if this is sun, Mercury starts from here, it goes in there, and then it doesn't come back here. Instead, it goes a little bit off, right? So is that clear? So this is called the precession of perihelion. Perihelion is the extreme point of the ellipse, so it precesses. Now, so it's a good story in a sense. By 1850s, right, the astronomical observations were accurate enough, so accurate that you could guarantee that yes, Mercury is moving on a yearly basis, and it is only tiny. I mean, about 1/60th of a minute or something. So divide the sky into 360 degrees and take that 1 degree, break that into 60 divisions. So it's pretty accurate there, and we are very sure about that by 1850 that Mercury is doing. And during the same period, it also turned out that by the time Pluto has not yet been discovered, right? Pluto is around that, I think between 1850 and 1950. I don't know. I mean, it's a big range, 100 years. Right? I really don't know when Pluto and Mercury were discovered. Surely it is before 1905, right? Because Einstein's equations depended on, or Einstein predicted this. Anyway, so the point is that they were so good at this prediction or matching observations with Newton's equation that they used to bring in Jupiter's contribution, and Jupiter, because Jupiter is there, it will have a change in the orbit by so much amount. And to the extent that just by observations alone, they could predict that there is a planet Pluto. Imagine again, they don't know about the existence of Pluto, but they notice that, Neptune is not behaving well, right? So there must be a planet there. It has to be there. And they predicted it, and they figured out that, there is such a planet. So it was very common in those days, in 1850s, that, something is missing, there must be something else. There is an external effect there. We don't see it because we don't have the tools to see it. So predict it, and then you go and focus it there, and you find it. So that was very common. And in this success story comes Mercury, and Mercury is getting shifted constantly, and which cannot be explained by Newton's law. What do? You again predict a planet. So this time, not outside, you predicted that the planet is very close to the sun. It is so close, and it is so bright, sun is so bright that we don't see it. And it is given a name. Even today, they talk about that in most of the fiction, science fiction movies. You will see that that planet has an up. Is this a V? Probably not, but not Vulcan. That's a Star Trek. I don't remember. Okay, so anyway, they predicted that there is a planet inside the sun that was convenient. So give it the sufficient mass, and you could explain this, and you are satisfied. But then you searched for it forever, and you didn't find it. So, but then came so my point here is that one way to explain this is that there is a perturbation. A perturbation due to, so it's a two-body effect. Two-body doesn't show this. A third body can bring in this. So bring in a third body. Or what happened is that, they didn't find the planet. They couldn't explain it using any of this perturbations from the other planet. It was Einstein who came and said that even a two-body problem, if you bring in relativistic effects, has precision. So just a two-body problem, in Einstein's way of looking at it, basically relativistic physics brings in a precision of the perihelion. But in those days, it was not precise enough. When they measured it, there was still a cushion. This was not what really proved Einstein was right, because it was, this is a pretty precision experiment you have to do. It is a third decimal or so. So it was not convincing enough that this is what it could. I mean, they could always say that, it might be this planet. that planet. So it's a little, it's not as clean as other experiments that gave it. It is basically the bending of light that was very clean, and that gives the general relativity really good. What we will do here is that we will talk about this, but as a perturbation, not using Einstein's theory, but using a small perturbation. We will show that next week, that we can explain this, or we can predict this perihelion shift. Right, that will be, I'll do it in the class, and you will do a homework problem also on that. I will do it for one perturbation. You pretend that it's another perturbation, like I pretend that I will say it's a Jupiter or something, or some order basically. It's not that, it's not important which planet it is. It is 1 over r raised to cube or 1 over r raised to 4. So I will do it for 1 over r square or cube, and you do it for r 4 or something like that. So that's something that you will see. So good point. So A is not conserved if it's not a two-body problem, and if it's not Newtonian. So good. Okay, so we want to write the Lagrangian for this two bodies. So there are how many variables? So there is R1, that's three coordinates there, and R2. And Lagrangian depends on velocities also. So that is dr derivative, right? So dr1 by dt and r2 by. Is there an explicit time there? Is there an explicit dependence on time? No, the potential energy here will be, oh, this is wrong, right? What's wrong with this?
Doesn't have direction.
Yeah, it doesn't have a direction, and even the dimensions are correct. Okay, sorry, dimensions. Yeah, it doesn't have a direction. I when I was seeing it from here, I thought I wrote the dimensions wrong. Okay, otherwise we would have caught it. Yeah, we change it so that, yeah. So this should have a direction, right? So there's some r hat, which let me say r1 2 hat. Just basically it's the direction. Yeah, it doesn't have a direction for sure. That was a mistake, but I also thought this was R. I wrote it as R. Okay, so it's not as bad as. Okay. So there is no time dependence in this interaction. So there will be no T in this. So one variable at least goes away immediately. And it's what will be the Lagrangian? It's a kinetic energy. There's two kinetic energies, M1 V1 square plus V1 dotted with V1, right? That's two vectors dotted with each other. And that is half M2 V2 square. And that is a potential energy which you have to subtract. Potential energy for gravitational force is negative Gm1 M2 over R. So it's a negative because it's an attractive force. So I have to add that because Lagrangian is kinetic energy minus the potential energy. So it is G M1 M2 over, what's this here? Is it R? Which R? Is it R1 or R2? So there are two. So this is R1, let's say. There's some origin. That's your R2. Right. So which one is it? Is it R1 or R2? It's R1 minus R2, right? It's a difference between them, and it's a length between them. So it's R1 minus R2, and it's a magnitude of that. Right. That's your Lagrangian. And move this. So as your M1, M2, there's an origin there, R1 and R2. First thing you do that, there is a center of mass of the system. So think of somewhere here is the center of mass of the system, correct? And around that, these two are moving. So usually these two body problems can be broken as a motion of the center of mass plus the motion of the two bodies around the center of mass. And if they're rigid, then that helps too. But let's say this. But before that, that question leads to the idea that where is the center of mass of Earth and Sun? How far is it from sun? Is it inside the surface of the sun or is it outside?
Should be inside.
Should be inside here. That's probably a good guess. What about Earth and Moon?
Closer to Earth.
Closer to Earth, but is it within the surface of Earth or not?
I don't think it is.
It is inside Earth. Yeah. Or now that you confuse me, check it till I'm curious. Yeah, check it. It's easy to work it out. At least I always find it surprising. Oh, it is inside. Yeah, I think it's inside Earth. Yeah. Yeah. So, because again, Moon is about 10 raised to 22, 10 raised to 24. And but here the distances also comes in, that's 400 times the radius of the Earth. So yeah, it's not very deep inside, but yeah, probably inside. But yeah, check on me. Yeah, that's the impression I had. Okay, so what's the center of mass? So change the coordinates. That's what we will do. So R, let's define, instead of working with R1 and R2, let's say capital R is equal to M1, R1 plus M2, R2 divided by M1 plus M2, right? That's your center of mass, but I'll write it here, M1 plus M2. Capital R is the center of mass, and let me have small r to be R1 minus R2. And let me change the whole coordinates. Now I want to write the Lagrangian in terms of these two. It is clear that this is R, that makes it simpler. Now we have to do V1 and V2, right? So solve for R1 and R2, we want to rewrite this, right? So what is R1 in terms of capital R? So if let me do this R2 first, right? Maybe R2 will be, I want to multiply by M2 here. So that cancels out. So this is M1 plus M2. No, so now I'm doing R. R2 is getting cancelled, so it is R1, right? M1 plus M2. And so it is M1 plus M2 times R plus M2 times R divided by M1 plus M2. So this is nothing but capital R plus M2 over M1 plus M2 times small r. Okay. Subtract them by after multiplying with M1, that goes away. So if I subtract them, so it is R minus of M1 over M1 plus M2 times small r. That's your two equations for R1 and R2. We are interested in V1 and V2. So what is V1? Vector V1, that's a derivative of this. So that's R dot plus M2 times, let me write that as capital V, why not? Capital V plus M2 over M1 plus M2 times small v. Capital V is dr by dt, and small v is small dt. So V2 similarly is capital V minus M1 over M1 plus M2 times velocity. We are interested in the kinetic energy of this whole system. So we have total kinetic energy will be, we are interested in half M1 V1 squared plus half m2 v2 squared. So square this. So this is half of m1 times v plus m2 over m1 plus m2 small v squared plus m2 minus square. What about capital V? That is a m1 v1 square, and this is a m2 v2 squared. So this is equal to half m1 plus m2 capital V squared. That's one term. The cross term is, notice this is m1 times m2 and this is m2 times m1. So the cross terms cancel out. And the small v has this coefficient, m1 times m2 squared. So the small v has this coefficient half of m1 m2 squared over m1 plus m2 squared plus m2 times m1 squared divided by m1 plus m2 whole square, and the small v squared. That cancels away. M1 plus m2 has a common factor there, m1 plus m2. After that, what is remaining is m1 m2 divided by m1 plus m2. So that's equal to v square plus half m1 m2 divided by m1 plus m2 v square. This quantity here can be written in the following way. Notice that 1 over mu is equal to 1 over m1 plus 1 over m2. Then you have, that's the same as m1 plus m2 divided by m1 m2. So mu is m1 m2 over m1 plus m2. So one can write this kinetic energy as half m1 plus m2 times the velocity of the center of mass plus half mu times velocity, the relative velocity between the two masses, and mu is called the reduced mass. So that's some algebra. What we did is that we transformed from R1 and R2 to the center of mass coordinates. So let's rewrite this equation. So our Lagrangian now is dependent on R, center of mass coordinates, relative coordinates between the two masses. And you would like to say this is dr by dt, and dr by dt, that's your velocity. So this is your v, capital V, and that's your small v. And your equations are half, let's call this capital M here. So this is capital M. So it is capital M velocity squared, the center of mass velocity, plus 1 by 2 mu velocity squared, and plus G M1 M2 over R. Notice that the interaction has nothing to do with this coordinate. The interaction is completely determined by the relative coordinate. So this is pretty much independent. That is just a uniform thing that's always there. If you start with a certain velocity, it will stay there. So it's convenient to choose velocity v to be equal to 0. How do you choose that? You go and sit on the center of mass. Right? You use your observation or your lab setup to have a setup so that they are on the center of mass. Then that is 0. That's not. It doesn't lose any generality. Right? This is not taking away any generality that should be. This is not for simplicity. It's just convenience that you do that. And after that, what you have is Lagrangian. As now there is no R. There is no R appearing in here, right? So this is gone because R doesn't appear in the problem at all. This one is a choice. So what we are remaining with is R and velocity V, relative coordinates and relative velocity. So if we started with 6 coordinates, suddenly we have brought it down to 3. Right? So and this is the relative velocity associated with it. So it is mu velocity squared plus G m1, m2 over R. That's what we will start from next time. We will now next say that angular momentum is conserved. We will bring this down from 3 to 2 and then use basically the planar idea and replace time with the angular coordinate. So it will be primarily it would be a 1 parameter problem with respect to the angle R and angle with the problem. We'll do that next time. Thank you. Questions?
So I had read
Mm-hmm.
that